Okay, so we've been looking at how we can figure out the vapor pressure if we've added a non-volatile covalent species. We've looked at how we can calculate the vapor pressure if we add a volatile covalent species. Our last piece to talk about is if we add a non-volatile ionic species. And so our last kind of example here, and this is the last type of problem we can see for these, is actually how we can start to figure out what happens if we add something that dissociates into more than one thing. And oh, there it is. Guess who's back? It's the Van Hoff factor. Now, if you're thinking about the two formulas, we'll hit this again here in just a second. Really, it's the same formula. All we're doing is taking into account the fact that every salt particle you put in is going to split into multiple ions that increase, and each single ion increases the amount of tractions in the solution. Less solution gets less solvent then gets to escape into that vapor, and as a result, we see an even greater decrease in the vapor pressure above the solution. So again, the math is pretty straightforward here. It's going to be just the addition of this Van Hoff factor. So let's take a look at our example here. Probably should have left us a little more space, actually, as I'm looking at now, but we should be able to get things taken care of if we kind of use our space appropriately. As we're looking, the first piece that jumps out at me is that we need mole fractions, and we do not have moles whatsoever. I see this 10.0 grams. We've got 10.0 grams of our calcium chloride. If we look on the periodic table, we can find its molar mass. I believe we've got a molar mass of 110.98 grams per every 1 mole. When we do that math, we get the moles of just our calcium chloride, which comes out to we've got 0.901 moles of calcium chloride. Cool. We're also going to need the moles of our water, which we don't have, but we do have its density. We've got its density, which is all less than 1. Oh, that's because it's heated up. At higher temperatures, our particles expand, and as a result, we see a decrease in the density. And we also have our volume. Well, I think we can work with those. A couple different ways you can do this. If you want to set up the density equation directly and use that to then change it into grams, and then once you got grams, change it into moles, you can do that. You could also use the density as a conversion factor, and that's what I'm going to do just to give us a different kind of look at this. So we've got 125 milliliters, right? Yeah. We've got 125 milliliters of water. And I know per my density, for every 1 milliliter from my density, we've got a mass of 0.996 grams. Oh, but I gotta take it a step further because I need to get to moles, and I know that for every 18.016 grams from the periodic table, it is equivalent to 1 mole of water. We do all of that, and we can find that our moles of water come out to be 6.91 moles of water. Cool. I think we've got everything we need to actually then solve for what we need. We've got our moles of solute. We could find our total moles by, excuse me, sorry about that. Come on, undo. By adding our moles together and then multiplying by our pressure and then including this Van Hoff factor. Speaking of, we look at our calcium chloride. So group 7 is soluble with everything except PMS. So this is soluble. It's going to dissociate into 3 particles. The Van Hoff factor, the I, would equal 3, 1 calcium and 2 chlorides. So if we want to solve then for our change in pressure is going to be equal to our moles of solute, which was at 0.0901 mole, over the total moles, which is the 0.0901, plus the moles of water, which was our 6.91. Moles on top, moles on bottom, they're going to cancel, leaving us a unitless fraction. We'd multiply by the original pressure of the solvent, which was our water. We could totally leave it in millimeters of mercury. That's not going to hurt anything here. We got 31.8 millimeters of mercury. I think it's going to be our unit here when all is said and done. Then we need to multiply by our Van Hoff factor, which for this problem we said was 3. When we go ahead and solve all of those pieces, we end up getting a value of equals 1.2279. So here's how much pressure is going to change. To figure out what the new vapor pressure is, then we're going to take our original pressure, which was that 31.8. We're going to subtract by our change, 1.2279, and we get our change in pressure, our final pressure, excuse me, which comes out with decimal places, 30.6 millimeters of mercury, which is a significant difference, mostly because we had a Van Hoff factor of 3 times its overall effect. So now as we start to think about what this means for us, as we start to look at our problem, when we come across these types of problems, we need to be able to identify which of our kind of formulas we're going to use. Now, again, the good news is these two are kind of the same. If you remember, this was for our non-volatile covalent species. This was our non-volatile ionic species. The good news is that for a covalent species, your Van Hoff factor is 1. So you could theoretically just use that last formula for both and just include the one for your covalent. That is entirely up to you. Really, the one that we got to watch out for is how we solve for the change in pressure directly. And that was for if we have a volatile covalent, how we would have to add the pressures and for both our solute and solvent together. Cool, this is the last of the information for the unit. We're going to be practicing and making sure that we're okay on these types of calculations. We'll be looking at some more example problems and just making sure we're doing okay.